In the last unit, we learned about how electrons are arranged within atoms, and now we're going to start talking about how atoms actually combine to start forming everything in the universe. So, we're first going to look at the three main types of bonding, one of them being ionic bonding, covalent bonding, and then something we'll show briefly towards the end of this, metallic bonding. Ionic bonding results when an electron is transferred from one element to another, resulting in oppositely charged particles that will then have an attraction to each other based on Coulomb's law. So in this case, you have a metal reacting with a nonmetal. And I can say that I know that it's a metal because once it reacts, it forms this lattice structure where you have the red becomes positively charged and decreases in size. That's what happens when a metal loses an electron. You have a decreased amount of repulsion as it loses a shell, and it becomes smaller. The nonmetal component, which has a higher electronegativity and higher electron affinity, will gain that electron, become negatively charged, and expand. So now they have increased repulsion, get larger. And what they do is they form this ionic lattice. So it's not forming a true molecule in the sense of what you think of when you see like water or any other molecule you learned about in biology. It forms this big lattice structure of alternating positive and negative ions. And these things are held together by Coulombic attraction between those oppositely charged particles. Covalent bonding is completely different. That happens when you have two elements of similar strength or similar electronegativity. It's going to be nonmetals and some metalloids. But you have two atoms combining and sharing electrons. And when I say sharing electrons, these are just positively and negatively charged things. And when you have these, the nuclei are repelling each other, and then you have one atom's nucleus attracting the other atom's electrons, and that other nucleus attracting the other atom's electrons. Basically, they end up competing for these electrons. And when you have a sharing, you have the electrons spending most of their time in the middle of those two atoms when they're being shared, as opposed to being transferred like you would have in an ionic bond. So, types of bonds. Metals and nonmetals, ionic. It's an electron transfer. If you have two nonmetals or some metalloids, you have covalent. That would be a sharing. And then when you have metals, you have metallic bond, and we end up with something called an electron C that there's a nice visual of later on. So just to revisit the term electronegativity, that's the strength an atom has when attracting electrons in a bond, as we've already stated. Nonmetals have much higher electronegativities. They're good at competing for electrons, and that has to do with their effective nuclear charge. The metals are very poor competitors when you're looking at fighting over electrons. So when you have something that's really weak with something that's really strong, the strong thing, the nonmetal, will pull the electron away. And so what we're going to do is we're going to look at the difference in electronegativities between these atoms to determine what type of bond will form. If you have completely covalent or nonpolar covalent, that's when you have two atoms of equal strength. That means the electrons will spend their time shared completely evenly and distributed the same around each of the atoms. We're going to use this difference as a guideline because it's actually not as important as the rule we just saw on the other slide of metals and nonmetals being ionic and two nonmetals being covalent. But polar covalent bonds form between two nonmetals, or metalloids, involved, where one is significantly stronger than the other and pulls the electrons closer to it. If you're looking at this molecule right here, this atom has the higher electronegativity and is pulling the electrons away from this other atom. So then this one develops a partially negative charge as it has a higher electron density around it, and this one develops a partial positive charge because it's now devoid of some of its electrons that it had as a neutral atom. And then ionic bonds are when there's a huge difference, 1.7 or greater, where the highly electronegative element steals the electron from the non-highly electronegative element. All right, so ions is what we're going to focus on in this unit. So we're going to look at, these are some of the main group elements, and these are the charges that they form. Alkali metals form +1, alkaline earth metals form +2, +3, and then plus or -4, but don't really worry about that one. -3, -2, -1, no charge for the noble gases. All right, so these ionic structures that form, they can form, again we said alternating positive and negative ions in this lattice structure, but it doesn't always have to be 1-to-1 like you would with sodium chloride. You can also have a 2-to-1 ratio like you would in calcium fluoride. And there are other ratios that exist as well. And these will determine the shape of the lattices that form, but we're not going to get into too much detail about that. The one new term you need to know when we're talking about ionic compounds is what a formula unit. Now, when we're talking about molecules like water, you have a beginning and an end. A formula unit is really the lowest whole number ratio of the ions present in the crystal lattice. And usually you list the cation, you always list the cation first and the anion second in that ratio. So here, since it's 1-to-1, you say NaCl. You don't say Na trillion, Cl trillion. All right, pause. So in the last slide, we looked at the ionic lattices that ionic compounds form. And we talked about them being held together by Coulombic attractions, which utilize Coulomb's law, which states that the force of attraction is equal to some constant times the charge 1 times the charge 2 divided by the distance between them squared. And we're not actually going to have to do any calculations and get an actual numeric value for forces of attraction. But what you really need to know is that as the charges of the ions increase, the force of attraction increases. And you need to know that the further apart the ions are, the less the attractive force is. So when you have larger ions, on average, the distance between them is going to be smaller, and that will lead to a decreased force of attraction. So just looking at these two ionic substances, you have sodium chloride, which is +1 and -1. According to Coulomb's law, the numerator is not all that large. These atoms are all approximately the same size, or ions are, relative to each other, approximately the same size. So size isn't going to be the huge impact here. But you can see that you have a +2 ion for magnesium and -2 charge for oxygen. And you can see that the melting point is substantially different. Now the melting point is the point at which the substance has enough average kinetic energy to overcome these static or forces that are holding everything static, giving this enough vibrational energy to move around and break apart this lattice structure, which is what happens when something melts. This requires a substantial amount more energy, and that's a result of the magnitude of the charges of the ions. So when comparing these things, looking at the first two, you have the other thing coming into play. Sodium's the same, but the difference between these two compounds is this one has chlorine and this one has bromine. Bromine is one level lower on the periodic table and therefore has a greater atomic radius or ionic radius. So the distance between the charged particles is a little bit greater. And you can see that the lattice energy, which is technically defined as the energy released when a mole of ionic compound forms from its ions in gaseous state. But you can also think of it, if you take the absolute value of it, is the energy required to pull apart this ionic lattice. So it takes less energy to pull apart the sodium bromide because the distance between the ions is slightly greater than it takes for sodium chloride. Comparing these two, you can see that calcium's the same. The difference is fluoride's -1, oxygen's -2. Since the magnitude of the product of their charges is greater here, it takes more energy to pull apart. And I'm going to ask you some other questions for you to analyze in the video after the fact with regarding those ones. All right. So this is another nice chart. What this does is it shows, these are the halogens ranked in order of increasing ionic radius. And here are the alkali metals, starting with lithium being the smallest, sodium being the middle, and then potassium being the largest. And you can see that the energy required to take apart sodium and iodine is greater than potassium and iodine. And this has to do with the fact that potassium is larger than lithium, and therefore it requires less energy to pull apart. Pause. And now I want you to answer some questions that I'm going to ask in the outline with respect to this graph. Lastly, we're going to talk about metallic bonding. So metallic bonding basically results from you have the protons and the inner shell electrons stationary in place. And then you have a sea of electrons that moves around, move freely. Work. Here we go. Bam. Play. And you can see that the outer shell electrons, or valence electrons, become delocalized. And that's what makes metals such good conductors of electricity. The fact that the electrons can flow. And if you actually apply an electrical field, what's going to happen is, if you put a positive charge over here, it's going to draw the electrons actually towards it, thus conducting a current. So all you need to know about metallic bonding is that it makes a sea of electrons. In the next video, we'll talk briefly about alloys that can form.